finish doing some actual stuff. Okay, so I'm recording. I'm going to share my screen. No idea what's on my screen. There we go. Okay, so new chapter, new section. We're going to do the stuff that we were going to do yesterday. And maybe what we'll do is we will wait until Wednesday, because Wednesday's really a Thursday schedule. So then we'll have guests with us again and we can go over the lab experiments, okay? Because I'd rather she be here to join us. So what we're going to talk about now is chapter 13, which is on gravitation. We will come back into chapter 12, but chapter 12 is really easy. So I thought it would be something to save for the end in case we're in a hurry. Chapter 13, which is this, and then the next chapter that we'll do is on simple harmonic motion. I don't know what the number is. Are different, okay? They don't, in the first 8 chapters, 9 chapters, we really kind of followed this progression. Everything was linear motion, and we covered everything in linear motion. 10 and 11 were, let's take everything we did in 1 through 9 and now make it go in a circle. Gravitation and simple harmonic motion will take some of the principles that we've talked about, but not all of them. So it's just different. They're kind of their own little topics over here, okay? But there will be things that you recognize. So just a little historical background. 1665, Isaac Newton makes his breakthrough realization that the same force that pulls the apple from the tree, I don't think it really actually hit him on the head, is what makes the moon orbit around the Earth. And this force is called gravitation. And it causes all bodies with mass to be attracted to all other bodies that have mass. And Newton came up with a law that brings this all together. And it's Newton's law of, and in astronomy we usually call it universal gravitation. And the universal part means that we feel that it holds everywhere in the universe. That no matter where we look, this principle is being upheld, okay? And it basically says that every particle attracts every other particle with a gravitational force whose magnitude, Fg, is given by G, capital G now, m1, m2 over r squared. And remember that when we are learning to write things in physics, we're really learning to write in another language, okay? So if this is a capital G, you need to make it a capital G. Don't make it look a G like this, because that's a big G as opposed to a little g. Don't do that. Make it look like a real capital G, okay? So M1 and M2 are the masses of the 2 particles that we're talking about. They are separated by some distance r. If we have more than 2 particles, which we'll talk about in a couple minutes, we might very well call that R12 because it's the distance between particles 1 and 2. Big G is what we call the universal gravitational constant. And it is equal to 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. This will probably be on the front of any exam you will ever take, including the AP. So you probably don't have to memorize it, but you might end up doing it inadvertently. I will always give it to you, and I'm almost positive, I'm 99.9% positive it is on the list of constants you get for the AP exam. Okay. So this is an attractive force, and only an attractive force. So the force of particle 1 by particle 2 and the force on particle 2 from particle 1. Okay, those forces are equal in magnitude and opposite in direction. Okay. So if that is true, what else can I call these? They are equal in magnitude and opposite direction and act on different bodies. It's a third law pair, excellent. Okay. So as far as we know, well, that's not entirely true, but gravity is never repulsive. Gravity is always attracted. So you should all, in the absence of any other gravitational field from the Earth, you should all clump up in the center of the room eventually because you're all pulling on each other. Okay. The universal law of gravitation is an example of what we call an inverse square law, which will pop up again and again and again and again if you go on to take engineering or any other physics class or be a physics major in general. Okay? So an inverse square law means usually that the distance between the objects squared is in the denominator. So as you pull things farther apart, that force weakens not just proportionally to the distance, but proportionally to the square of the distance. Okay. Other examples of that is the force between two charged particles. Okay, works that way as well. And that is something you would get in the second half of this class, which I am not teaching. Okay. So this equation is designed for particles or objects that are separated such that the distance between M1 and 2 makes M1 and 2 look like point sources. Okay? So this isn't an equation that would work for Eva and her computer. Okay? This is an equation that would work for Eva and Miss Banks in the computer office. I'm trying to think of something that's very far away. Okay? They would appear to be point objects between each other. Okay? And what that means, again, is just that the it acts equally like on all parts of it. Okay? We don't have to worry about the extent of an object. Okay? And if we do that, then we would say that this gravitational force would act on Eva's center of mass, okay, and would act on Miss Banks' center of mass. Okay? We'll talk a little bit later about the difference between center of mass and center of gravity, but unless you're very near a black hole, they're going to be in the same place anyway, so we're not going to worry about it for practicality. Okay? Sorry. Been sitting like all day, and it's just I can't do it. When we talk about things near the surface of the Earth, because obviously the Earth does not look point-like to you, okay? When we talk about that, we use something called the shell theorem, which was in your book. And basically it means that a uniform shell of matter is equivalent to all of the mass that's in there being concentrated at the center when you look at it from the outside. I'll write it down. I'll type it out. Okay. your mask on. I could see it coming through your eyes. Okay. So that means that if I had a shell, so think about like a hollow ball, okay, like a rubber ball, that would behave as if all of the mass in the shell part, in the outer part of the rubber ball, were at the middle. So if I want to talk about what to do about the Earth, if we assume that the Earth is uniform, which it's not, we'll talk about that a little bit in a minute, and you'll do some homework about that eventually. But right now we need to get through the chapter 11 homework and put that off our plate before I assign more. Okay? So we assume that the Earth is uniform, and we just break it into all these concentric shells. And then we assume that all of the mass in the outermost shell is in the center, and the mass in the medium shell is in the center, and the mass in the inner shell is all just concentrated at the center. So we can consider the mass of the whole Earth to be concentrated at the center. Okay? And so if I wanted to find out the Earth's pull on you, I would pretend that all of the mass of the Earth was at the center. You're standing out at the radius. I would use this formula over here. M1 would be your mass, M2 would be the mass of the Earth, R would be the radius of the Earth. And we'll actually do that in a minute and figure out what little g is. Okay? All right, it's just kind of a construct, okay, that matters in other situations and not that much to us. Okay? So I alluded a couple minutes ago that we could have a situation where we had more than one mass. And if we do that, then we use something called the superposition principle, which you are very familiar with. We just haven't called it that in a long time. Okay. So the superposition principle means that if I have three masses, so I've got some M1, and I have some M2, and I have some M3, and M1 and M2 are separated by R12, and M2 and M3 are separated by R23. And I want to find the gravitational force, so find the force on, say, M2. Okay. I know that F3 is going to pull that way. I know F1 is going to pull that way. I know we kind of talked the other day about how you name things with subscripts, and it doesn't really matter as long as you're consistent within any given problem. So you could let the first number be the number of the object that's being acted on, and you just have to be consistent about it, okay? So we could figure out the magnitudes of the forces just by using the rule. But then I would find whatever that net force was on particle 2 by adding vectorially the forces from each of the components. Sorry, the forces from each of the other masses, okay? And if I had more masses, I would just keep adding more and more numbers, okay? Okay, we good? We'll do an example in a couple of minutes. So let's talk about calculating little g. Okay, it's a value that we've been talking about all year. We've been using it. It was presented to you as a Here's the acceleration due to gravity. Okay. Some years we're able to measure it with a picket fence. We didn't do that. I didn't think we did. Did we? When we dropped the thing with the black marks on it.
Oh, yeah.
Yeah. Okay.
For some reason, when you said picket fence, it's an actual picket
Oh
fence.
yeah, no, it's just called a picket fence.
No.
It's just called a picket fence. Okay. So you measured that there experimentally, but you were comparing it against an actual value. Okay. That can actually be derived. So we're going to consider a particle that's near the surface of the Earth. Okay, and it's going to be some distance r from the center of the Earth. And the force acting on that particle, we call it F capital G. And actually, I had some students several years ago who convinced me that we should call it F capital G because F little g is mg. And this has a different equation, so we'll call it F capital G. And that's going to be G, capital G, the mass of my particle times the mass of the Earth divided by r squared. And remember that as long as I'm outside of the Earth, I can just take a whole bunch of concentric shells and assume that all of the mass is concentrated at the center. Okay. So at the same time, I can also apply Newton's second law. I can also say that F net is equal to ma. Now, if we ignore air resistance and all the other stuff, then the only force acting on my particle is that gravitational force. And the acceleration that it feels is ag. Okay. And there are obviously the acceleration and the gravitational force are going to be in the same direction. And so I can say this is g m, mass of the Earth divided by r squared is going to be m times ag. And then as you can see, I can cancel little m, which is what we've talked about from the beginning, that it doesn't matter whether I drop a mouse or an elephant. They're going to fall with the same acceleration if I'm ignoring air resistance. They're going to behave the same way. So that tells us that ag, which is g, the acceleration due to gravity, is going to be g, the mass of the Earth, divided by r squared. And if we're close enough to the surface of the Earth, basically r is going to be the radius of the Earth. Okay, so that's going to give us 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And the radius of the Earth is 6.37 times 10 to the 6th meters squared. So what do we get? You calculate that. I desperately need a drink of water. This is my second hour and a half. Yes.
Is that 5.98 times 10 to the 24?
24.
Okay.
What'd you get, Dagny?
9.83.
9.8 what?
9.83.
Yeah. I believe the accepted value that they used to publish in the old Regents tables was 9.81. But
That's what we use fractions for this, and that's what I call like first time last year, that's class, like that's name 9.81.
you can use 9.81, but so many.
This equation is also universal, so like we could apply to other lines.
Yeah.
And
Yes.
Does this apply only in our solar system or?
No, there's nothing, no. It's based on theory that we believe to be universal. So when your space, no matter what planet and what solar system your spacecraft crashes on, you can use this to find the acceleration due to gravity on that planet, which leads you, as you'll eventually see, to be able to figure out what your escape speed needs to be. Or it might be that you'll be able to figure out the mass of the planet, because perhaps you can measure whatever the acceleration due to gravity is another way. You know, dropping things, or actually, when we get to simple harmonic motion, you can actually use a pendulum to figure out what the acceleration due to gravity is. And now you could find the mass of the planet, which would lead you to be able to figure out what your escape speed needs to be.
Use that to find the radius of the planet?
Yeah, but there are ways to find the radius of the planet, other ways. That we talked about in astronomy, actually, last year, because I was able to do those things last year, where you measure where the sun is at different places at the same time and do some shadows and stuff. So, okay, so this makes some assumptions. It assumes, number one, that the Earth is a sphere. The Earth is not a sphere. The Earth is a squished basketball, okay? The distance between the center of the Earth and the poles is smaller than the distance between the center of the Earth and the equator. It also assumes that the Earth's mass distribution is uniform, which is not true. Aside from the fact that there are things like water and land, aside from the fact that as you drill down, you go through different kinds of materials. Anybody who's ever used the Hubble Space Telescope will tell you something funky happens over the Indian Ocean, and it messes up the gyroscopes in the Hubble Space Telescope, and you don't want to have your observing time for when it's over the Indian Ocean, because everything will be messed up and your data won't be worth crap. Just saying, okay? So it makes some assumptions that you can, it makes some assumptions. It also assumes that the Earth doesn't rotate, and we know that it does. And that's going to add, because that's going to give you a what? If you're on the Earth and it's rotating, you also have what kind of acceleration? Centripetal, okay? So that's going to affect things as well, but not enough. But it does lead to variations in the acceleration due to gravity as you move around the Earth, but not enough for our purposes. Okay? It's not going to affect Guess in China if she uses 9.8 meters per second squared. Okay? If she was doing something where she needed to know G out to little g out to 6 or 7 decimal places, then yes, it might matter, but not for doing high school physics problems. Okay. All right, so let's try the example. So the example says 3 5.0 kilogram spheres are located in the XY plane. What is the magnitude and direction of the net gravitational force on the sphere, which I think I labeled as B, at the origin due to the other two spheres? Okay. I've rewritten this problem many times over the years, so just have to see. Okay. So we've got a mass up here, which I believe I've labeled M3. Is that true? Okay, I have a mass here that's M2, and I have a mass over here that's M1. This distance is 0.30 meters, and this distance is 0.40 meters. What do you have? Oh, okay. Okay, we'll do it that way then. It's wrong, but it's not wrong. I typed it in. So this is 3.0 and 4.0. Okay. It'll change the answer, but only in order of magnitude. Okay. And then we want to find the magnitude of the force on M2. Okay. So we know that M1 is equal to M2 is equal to M3 is equal to 5 kilograms. And we have our R12 is going to be 4.0 meters, and R23 is going to be 3.0 meters. Okay. So if I want to find a force, what am I supposed to do first? Free body diagram, okay? So here's my M2. Remember that the gravitational force is always attractive. So this is going to be F21 pulling towards M1. This is going to be F23 pulling towards F3. And then somehow I'm going to add those together and end up with the magnitude. Okay, but I have to figure out what the magnitude of those forces are first before I add them together. So the magnitude of F21, G, M1, M2 over R21 squared. I know, we're all dying in here. I wonder what the temperature actually is.
My computer is definitely
82, 83. Yeah, it's 82, 83. So everybody's going to leave before the calc test, okay? Everybody's going to go and find some place to have a breath of fresh air, okay? So G is going to be 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. And then I have 5 kilograms times 5 kilograms divided by 4.0 meters squared. So what's the magnitude of F21?
It is a small number.
Oh yes, a very small number. A horribly small number. Even smaller than it normally would be because I put the decimal place in the wrong spot for the distance.
It is 1.0
Negative 6?
I got the negative 10.
Yeah, negative 10 sounds better. Okay. Yes, no, Fiona? Okay. And then we can do the same thing for F, what did we call it, 3.2 or 2.3? 2.3. Okay, so again, I have G, M2, M3 over R23 squared. Again, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. And again, that's how you get to learn constants like that, is you write them down every time. Okay? 5.0 kilograms times 5.0 kilograms divided by now 3.0 meters squared. And what do we get? Hmm. Should probably be 10 to the negative 10 for starters. And it should be 1.9. Okay. Okay. So these components happen to be perpendicular, making our lives a little easier, right? Okay. So we can say that the magnitude of our FG is just the square root of the sum of the squares. So that's going to give me the square root of 1.0 times 10 to the negative 10 newtons squared plus 1.9 times 10 to the negative 10 newtons squared. And what do we get? Okay, what did others get? Yeah? Okay. So let's just find the angle because I think it's magnitude and direction, and then I'll let you go. Okay. So remember that I'm adding these. So F, what did we call it? 2-1? F21 goes that way. F23 goes that way. So my resultant is here. And I, of course, want to know what that theta is. Okay. So, of course, I can say that tangent theta is opposite over adjacent. And you substitute everything in, and theta is 61 degrees. You guys should be able to do that easily, no problem. Okay. So go breathe somewhere for a little bit. Okay.